Welcome to class of Electrodynamics 1. In this class we will discuss the summary of second chapter, which is the electrostatics, and then we will discuss the electrostatics boundary condition. You know that we have studied the different formulas related to the Coulomb's law, Gauss's law, and then related to the electric potential, Poisson's equations and Laplace equations. We will summarize here, and we also look at how we can use to find out the different variables from these formulas. Suppose you have the volume charge density rho, and you want to find out electric potential from that. Then you will use this formula: V is equal to 1 over 4 pi epsilon naught integral rho over r deta. This is the volume integral over the whole charge distribution. And this is the basic general formula to find out the electric potential, where r is the separation distance, magnitude of the separation vector, and deta is the small volume element, and rho is the volume charge density, which is at this small volume deta. And if you have the electric field and you want to find out the electric potential from that, then you will use this formula: V is equal to minus integral E dot dl. This is the line integral, and line integral is taken over some path, and if you have that path and you know the value of the electric field at each point of the path, then you can evaluate this line integral to find out the electric potential. Next, if you want to find out electric field from the charge density, then you will use this formula: E is equal to 1 over 4 pi epsilon naught integral r cap over r square rho deta. This is the Coulomb law, where the rho is the volume charge density, deta is the small volume element, and r is the magnitude of the separation vector. In reverse, if you want to find out volume charge density from electric potential, then you will use this Poisson equation: del square V is equal to minus rho over epsilon naught. You can find out rho. Rho will be equal to del square epsilon naught del square, and then taking the product with negative sign, you can find out a volume charge density. And similarly, if you want to find out electric field from electric potential, then you will take the gradient of electric potential, negative gradient of electric potential, and you can find out electric field very easily. Similarly, if you want to find out the volume charge density from electric potential, then you will take the divergence of electric field, and you can find out volume charge density using the electric field. Now we will discuss boundary conditions. There are the two main boundary conditions of the electric field: perpendicular boundary conditions and parallel boundary condition. Perpendicular boundary conditions, I mean that these boundary conditions are related to the perpendicular components of the electric field. Now we discuss the perpendicular components of the electric field, whether these perpendicular components when passes through the surface charge are continuous or not. For this we take a surface charge sigma. This shaded area shows the surface charge, and we evaluate the Gauss's law to find out the electric field. We draw a Gaussian pillbox. Half part of the Gaussian pillbox is above the surface charge and other half is below the surface charge. This Gaussian pillbox has the cross-sectional area A, and this Gaussian pillbox has 6 sides. So we will apply the Gauss's law on this Gaussian pillbox to find out the electric field. And the Gauss's law is closed surface integral of E dot dA is equal to 1 over epsilon naught Q enclosed. Closed surface integral E dot dA is evaluated on this Gaussian pillbox, and this Q enclosed is the charge which is enclosed inside this Gaussian pillbox. Because the surface charge has the surface charge density sigma, and surface charge density sigma is defined as the charge per unit area. So if you multiply this charge density with the cross-sectional area of this Gaussian pillbox, you can find out the charge enclosed, which will be equal to Q enclosed is equal to sigma A. And left hand side of this Gauss's law is integral E dot dA is equal to because this surface integral is over the whole surface of the Gaussian pillbox, means this is a closed surface integral. For the upper surface, this integral can be written as integral E dot dA, and for the lower surface this integral is integral E dot dA, and for all the other surfaces which are the side surfaces, this integral can be written as integral E dot dA, and then we will find out the electric field. For this, because we are interested in the perpendicular components of the electric field, we take the height of this Gaussian pillbox very small, which is approximately equal to 0, which approaches to 0. So surface integral become 0 for the side surfaces, and this closed surface integrals now consist of these two surface integrals for the upper cross sectional area and lower cross sectional area. For the upper cross sectional area, this surface integral can be written as E dot dA, because for the upper cross sectional area, the perpendicular component of the electric fields and area A are in the same direction. So we can write the perpendicular component of the electric field multiplied by dA. And for the lower surface, which surface integral which is below this surface charge, we can write E dot dA is equal to minus integral E perpendicular dA, because for the lower surface, components of the electric field and area are in opposite direction. Electric field is in upward direction and area is in downward direction, so angle between the electric field and area is 180 degree. Therefore the negative sign arises for the lower surface. And for the side surfaces, these are the 4 side surfaces, and for all these surfaces, the surface integral becomes equal to 0 because area approaches to 0 for all these side surfaces as E approaches to 0. So the Gauss's law becomes closed surface integral E dot dA is equal to Q enclosed over epsilon naught. Left hand side of this Gauss's law consists of two surfaces integral for the upper and lower cross-sectional area of the Gaussian surface, and Q enclosed is equal to sigma A, and we can write E perpendicular above minus E perpendicular below, taking integral dA common here, is equal to sigma A over epsilon naught, and integral dA is the integral over the surface cross-sectional area of the Gaussian surface, and which is equal to capital A. So this capital A will be cancelled with this area A, and we get E perpendicular above minus E perpendicular below is equal to sigma over epsilon naught. Now we are going to discuss the tangential component of the electric field. For this we know that curl of the electrostatic field is always 0, and using the Stokes theorem we can write a closed line integral E dot dl is equal to 0. What we have done, we have taken a surface integral of this curl, and then we have applied the Stokes theorem, because Stokes theorem relates to relates the curl of electrostatic field is equal to closed line integral. So we can write this in this way here. Now we evaluate this closed line integral. So we must have a closed line. We take this closed line. This closed line has the four sides. The upper side, these are the two sides, and this one is the lower side below the surface of so this closed line integral consists of these three integrals for this upper line, for the below line, and for the sides. These are the side lines, these are the two side lines. So this closed line integral consists of these three parts. For this upper side, this line integral will pick the parallel component of the electric field. So E parallel above dl, E dot dl can be written as, for this upper side, E parallel above into dl, because these parallel components and length elements are in the same direction. And for the lower side, this can be written as minus integral E parallel dl. In this case, the electric field and length element are in opposite direction, because electric field is from right to left, and length element has the direction from left to right. Therefore a negative sign arises here. And for these sides, this has the length equal to E. This E is very less. This width approaches to 0, so this line integral goes to 0, and we can write this closed line integral in this way: integral E parallel dl above minus integral E parallel dl below is equal to 0. we take the common dl, integral dl from these two terms, and because the integral dl cannot be equal to 0, so E parallel above minus E parallel below is equal to 0. Here we summarize the boundary conditions, because this is the perpendicular boundary condition, which is not continuous because it is not equal to 0, and this is the parallel boundary condition that we have studied here. This is the continuous because it is equal to 0. If we combine these two boundary conditions, then we can write E vector above minus E vector below. This is the electric field above the surface, this is the net electric field below the surface. This must be equal to difference of these two electric field must be equal to sigma over epsilon naught, where this n cap is the direction perpendicular to the surface. To combine these two equations, we multiply this equation with n cap, because n cap is the vector perpendicular to the surface, and direction of the electric field is also perpendicular to the surface. Therefore, in vector form we can write this equation in this way: E perpendicular above n cap minus E perpendicular below n cap is equal to sigma over epsilon naught n cap. And for the parallel component above the surface, we can write this equation in the parallel form, and we multiply here with the x cap, and x cap here. And when you combine these two equations, then E perpendicular above n cap plus E parallel above x cap, this becomes a net electric field above the surface, and we denote it E vector above minus E perpendicular above n cap and minus E parallel below x cap. This will become a net electric field below the surface, and here sigma over epsilon naught n cap plus 0, this will become sigma over epsilon naught n cap, and in this way we get the net equation in the combined form. This equation can be written as. Now we discuss the potential difference across the surface. We take this surface and having the surface charge density sigma. Below the surface we take a point A, and above the surface we take a point B. We want to find out the potential difference between A and B. So potential difference can be written as V above minus V below is equal to minus integral A to B E dot dl. This is the equation that we have used in the second chapter when we studied the topic of the potential difference, and we take this path from A to B approaches to 0. From A to B this path is very less, so this line integral goes to 0, and we get V above is equal to V below. It means that potential above the surface is equal to the potential below the surface, but the gradient of the potentials are not continuous, and we write here E is equal to minus del V For E above, we write here minus a gradient of E above, and for E below, we write here minus gradient of V below is equal to sigma over epsilon naught n cap. If we multiply it with the negative sign on both sides, we get this del V above minus del V below is equal to minus sigma over epsilon naught n cap. Taking the dot product with n cap on both sides, uh, del V above dot n cap minus del V below dot n cap is equal to minus sigma over epsilon naught n cap dot n cap. N cap dot n cap is equal to 1. What is meant by del V above dot n cap? Because gradient of V means change of potential in maximal direction, and if we take the projection of this vector to n cap, it means change of V in the direction of n, and we can write this del V dot n is equal to curly V over curly n, mean rate of change of V in the direction of n. So we can replace this term with this curly V above over curly n minus, similarly we can replace this term with this curly V below over curly n is equal to minus sigma over epsilon naught into n cap. So this is the equation of the boundary condition for the gradient of the V.